And we are getting going, and I need to do a little bit more of these exercises on closure, and I want to do this number 8, and some of these are done, but I know that I've got to do number 8. In number 8, we are given a couple of open sets, A and B. And the closure of A is the entire number line. It means what? Every number is close to A. And the closure of B is the entire number line, which means what? Every number is close to B. And we want to prove that every number is close to the intersection of A and B. And I want to talk about this problem, and the first thing I want to say in a different color is note that if you take A to be the set of all rational numbers and B to be the set of all irrational numbers, then A bar and B bar, the closure of A and the closure of B, I'm trying to find that bar, A bar and B bar are both equal to the whole number line. If you take any real number at all and you put it in a neighborhood in a little stick, that stick will contain some rational numbers. That's something we know. I've been a little bit more murky about the set of irrational numbers, but we are, for the time being, for the sake of examples, we're certainly going to assume that if you take two different numbers on the number line, unequal to one another, that between them there are also some irrational numbers. So if you ever take a stick in the number line, there are rationals there and there are irrationals there. So every number is close to the set of rational numbers, and every number is close to the set of irrational numbers. And I want to point out, if you take the intersection of A with B, in this case you get the empty set. If you intersect the set of rationals and the set of irrationals, you will get the empty set. And so we definitely don't have this. Can't have that, because not only is A intersection B not big enough that every number should be close to it, nothing's close to it. A intersection B is possible, the worst case scenario, dead, got killed. You see, it's empty. And there are no numbers close to A intersection B. So I want to point out that you mustn't expect that just because you've got a couple of sets A and B, and every number is close to A and every number is close to B, that every number has to be close to A intersection B. But what did I say in this problem? A and B are what? Open sets. Oh, that's very special. This is how we're going to do it. I'll take out the words to do, if you don't mind. And we want to show that every number is close to A intersection B. That's what we have to prove. See? So I'm going to ask you a question. How do I go about proving that every number does some job? Suppose that X is an ice cream. No? Suppose that X is a number. The moment you get this language right, it will write the solutions for you. Suppose that X is a number. Right? Okay, folks, what must I do to prove that X is close to a set. What does the definition say?
For every stick, center x radius delta positive.
For every positive number delta, the stick center x with radius delta, next word, intersects with whatever set you're talking about. The set I'm going to be talking about will be, I can't find it. Here, will be that. Okay? So how do you prove that something happens for every positive number delta? To prove that something happens for every positive number delta, suppose that delta is a positive number. Right. Since x is close to a, how do you know? How do you know x is close to a? How do you know? Well, you have given information that every number is close to a. Well, my number is also close to a. See? If I told you every person in this room is a millionaire, it would be very nice because then I could conclude that I'm a millionaire. You see? Okay. So I know that x is close to a. Since x is close to a, we know, I know that the intersection of the stick center x radius delta with a must be non-empty. Isn't that right? The set, I'm going to take that stick and intersect it with a that must be non-empty. You see? I'm going to tell you something. Is a non-empty, I'm going to write it this way, because it also allows me to sneak in more information, open set. Isn't it open? Okay. So the set that I've just written, this set is a neighborhood of x, is it not? Okay. And since x is close to b, we now know that if you take this set and intersect it with b, that's got to be non-empty. I've got a number x that is close to b. And I've got a neighborhood of x. What does that tell me? That neighborhood must intersect with b. So I've just proved that this stick intersects with a intersection b. You see? So we have shown that x is close to a intersection b because I said, suppose delta is greater than 0, and lo and behold, the interval center x radius delta intersects with a intersection b. You don't have to put parentheses because intersection is associative. If you feel like putting in a pair, if it makes you feel better, do it. But you don't need them. Put them in, take them out, put them in, take them out, whichever you like. I said, what if only one of the sets A and B is open? Because you're given that A and B are open. What if you were given information that A is open and I didn't tell you about B? Is the result still good or is it in trouble? If you don't know that any of the sets A and B are open, then the thing can go wrong. You understand? So if one of them is definitely open and the other you don't know, is that good enough? Here I said if both of the sets are open, we're good. Well, if you look carefully at this yellow proof, let's read it. We want to show that every number is close to A intersection B. That was just a we want. Now we start. Suppose that X is a number. I want to show that X is close to what? A intersection B. Right. Suppose that delta is greater than 0. Okay? Since X is close to A, we know that because all numbers are close to A and all numbers are close to B. Right. Since X is close to A, this neighborhood of X must intersect with A. We know that this set is non-empty. What kind of set is this? It's the intersection of a known open set and a known open set. And the intersection of two open sets has always got to be open. Fair enough? So, this is a non-empty open set. I've used the fact that A is open, have I? Now, because this is a non-empty, because this set is a neighborhood, because this set is a neighborhood of X, is it not? Because this set is a neighborhood of X, it has to intersect with B. Do you understand? Is there anywhere here where it said B is open? No. So therefore, it was good enough to know that one of them is open. All right. What else do I want to do here? Nothing. I'll leave some for you. I need to talk about this topic. This is our main topic today. I want to talk about limit points. And I want to tell you something. We have been talking about a point being close to a set. Let me remind you, what does it mean? I'm just reminding you. A number, X, is close to a set A when what? When for every delta greater than 0, we have, let's say, the intersection of that thing with the set A is unequal to the empty set. And this is if and only if for every neighborhood of X, the intersection of that neighborhood with A is non-empty. Okay? So I'm going to say something to you here. I'm going to say definition. Definition of a limit point of a set. Limit point. Given a number, X, and a set, should we call it A or something? Okay. We call X here's the new word, a limit point. If you want to know how I typed that, I went down here and I selected definition bold as my font, and that makes the definition font. See?
So how'd you do it on the short one?
How did I? I'm not telling you. Okay. So we call X a limit point of A when X is close to A slash singleton X. This looks weird. Trust me. Just for the moment. Definition. A number X may or may not be what we call a limit point of a set A. What does it take? a number is called a limit point of a set when it is close to this set here. You say, this, you know what this is? This is the set A with the actual number x pulled out and thrown out of the window. It's what remains from the set A. Do you understand that this is a subset of A? So I want to say something immediately to you. Any number that is a limit point of a set A must be close to A straight away. Because in order for a number x to be a limit point of A, the number must be close to that subset of A. Now remember, a number that is close, if you have two sets, one of them a subset of another, any number close to the smaller set will always be close to the bigger set. Is that not true? If you know, here, I will take this out. I don't want to clutter the notes. But suppose you know, if we know, how do you spell know? If we know that, let's take two sets, I'll call them S and T, so that I don't make it look too much like the other stuff. If S is a subset of T, then every number close to S must be close to T. Why? Suppose that a number is close to S. If you take a stick around it, the stick contains members of S. It certainly contains members of the bigger set T. You see? I'm not leaving that in. So every number that is close to that set will certainly be close to the bigger set A. Okay? I want to give you an example immediately.
So X must be a member of A?
Doesn't have to be. Doesn't have to be. I'm glad you asked that, but I'm going to keep you waiting. I'm going to give you an example. Here we go. We define A to be the set consisting of the numbers 1, 2, and 3. And we define x to be 3. Okay? This number x is close to A because x belongs to A. Agree? However, x is not close to the set consisting only of 1 and 2, which is exactly A slash singleton 3. Whoops, what happened to my slash? If you pull 3 out of A, you get left with the set whose only members are 1 and 2, and 3 is not close to that.
What if we choose a delta that is big enough to be close?
The condition of close says for every. You see, just because you say, what if we choose? I'll choose delta to be 1,000,000. That won't help. Because in order for the number to be close, it doesn't mean that simply that you can find one delta that will make the delta stick contain points of A. No, it's got to happen for every. And so just because you've got a delta, a nice big delta stick that has points of A, That's cold comfort, because what about some other delta that was too small? Yeah, any number less than 1 or even equal to 1, you see. So therefore, there's no question that the number 3 is not close to the set whose members are 1 and 2. I'm going to give you another example. Here's another example. We define A to be the following set. I'm going to take the interval running from 1 to 3, union singleton 5. And I will show you what this looks like in a little picture. So here is the number 1, and here is a bit of number line, and here is the number 3, and is 5. You understand? Now, the number 5 is close to A, is it not? Because it actually belongs to A, right? And you're dying for me to answer your question, right? We're getting there. The number 5 is close to A, right? Because it belongs. But 5 is not close to the set 1, 3. 5 is not close to that interval, right? Which is A slash singleton 5. Do you understand?
What if instead of pulling out 5, you pull out the 3 and that is empty?
No. This is my example. My example. My example. I'll take another example later. I want this one. I'm boss here. I want this example. I want the 5. I want to show you how a number can be close to a set without being a limit point. Other numbers, no problem. This number, problem. See? That's why I'm insisting on this one. Okay, now, now I'm going to, back to the definition. There, I repeated it. Oops. I don't want this yellow stuff again. I rewrote the definition because I want it right next to me. A number x is called a limit point of a set A when what? When x is close not just to A, but to a slightly smaller set. So now I'm going to tell you something. A number x is a limit point of a set A if and only if for every delta greater than 0. So what is the condition that the number be close to that set? That for every delta greater than 0, the delta stick around x intersects with Charlie over here, right? The stick center x radius delta intersected with A slash singleton x is non-empty. See? I'm going to say this again in a different color. A number x is a limit point of a set A if and only if for every delta greater than 0 there is at least one number in this stick that is unequal to x and belongs to A. I'm stating it in this language. I'm really repeating myself. What is the condition that x be a limit point of A? Limit point of A. That for every delta greater than 0, there is at least one number in the stick that belongs to A and is but better than belongs to A. It belongs to this. So when you belong to A / singleton X, what are you if you belong here? You're a member of A unequal to the number X. So I'm saying for every delta greater than 0, there is at least one number in that interval that not only belongs to A, but it belongs to A and is not X itself. Okay? And now I'm ready finally to answer Mesa's question. First, I'm going to give an example. Here's an example. And I think I'll make you happy also. We take A to be the interval, let's take this interval running from 1 to 4. What the hell did I do? The interval running from 1 to 4. Okay? And x equals 4. Please note that x does not belong to A. And please note that x is definitely close to A. That we know. See? If you take a stick around the number 4, you're going a bit to the right. Who cares? You're also going a bit to the left. I care. You see? It picks up some stuff in that interval. Right? Okay. You want a picture? I can't give you a very good picture, but here is 1, and here is some number line, and here is 4. That's all I can do. If you take a stick around 4, it will pick up some red. Will it not? Right. Now I'm going to tell you something. We have the following equation. If you take the set A, which is the interval running from 1 to 4, and 1 is in, I don't care about that, but 4 is not in. You understand? I want to tell you something. If you take this set A and you put a set minus singleton 4, these two are exactly the same thing.
This 4 doesn't belong to the
Yeah. Let's read this. What does this stand for? It's the set of all the members of A unequal to 4, but the members of A are already 4. Let's suppose you had a certain room, not this room, the next room. And suppose you were told that every person in that room had red hair. It's not true in this room. I think we got a few counter examples. Okay? But in the next room, everybody has red hair. Okay? And then I say, the set of all the people in that room, with the exception of Jonathan Lewin. Isn't that the set of all the people in that room? Because I don't think anybody would pay me to copy Encyclopedia Britannica. Nobody knows what I said.
I know what you said, I just don't know what you mean.
You know what I mean.
You should say what you mean.
I am not going to tell you. Pick that up somewhere. Okay. It's a beautiful short story called The Red-Headed League. Okay. Somebody will look it up. Okay. So anyway, the number 4 doesn't belong to A. So the set of members of A that are not 4 is actually the set of all the members of A. Isn't that right? And so, I want to tell you that the number 4 is close to A slash singleton 4, because that's just the same statement that I said before, that the number 4 is close to A. You understand? Because this set is exactly A, right? Let's do better. Let's do better. We assume that A is a set of numbers. All our sets are sets of numbers unless I say otherwise. If I want a set of chickens, I will tell you. Okay? All right. We assume that A is a set of numbers and that X is a number that does not belong to A. Do you understand? Now we know A is exactly the same as A slash singleton X. Isn't that true? The condition for X to be close to A is exactly the same as the condition for X to be a limit point of A. What does it mean for X to be close to A? For every delta greater than 0, the stick center X radius delta intersects with A. What does it mean for X to be a limit point of A? For every delta greater than 0, the stick center X radius delta intersects with that set. But what did I tell you? I told you that X does not belong to A. So therefore A and A slash singleton X are exactly the same thing. Let me say, what does it take for X to be close to A? That every neighborhood of X intersects with A. What does it take for X to be a limit point of A? Every neighborhood of X intersects with that, right? But these sets are exactly the same. Therefore, for non-members, let me make this clear. For non-members of a set A, being close to A is exactly the same as being a limit point of A. You see? For non-members. But for members, it's not the same. Let's come back and let's have a look at this example over here. Remember this? I'm coming back to this example. What was this example? A consists of the union of this interval from 1 to 3 and singleton 5. So what numbers belong to this set? Who gets to belong here?
5.
All the numbers in the interval from 1 to 3, and one more thing. There's one more number that belongs to the set. Who else gets to belong here? 5. Right. So now I'm telling you, I'm looking at the number 5. 5 is close to the set because it belongs. Is 5 a limit point of the set? Not a chance. Because if you take a teeny little delta and you take the stick around 5, it's much too short to reach the good stuff down here. You see? So a member of a set, of course, will always be close to the set. You understand? A member of a set will always be close, but may not always be a limit point. You see? But a non-member of a set will be close to the set if and only if it is a limit point. Why? Suppose X is not a member. Suppose X does not belong to A. Well, A and A slash singleton X are exactly the same thing. So for every neighborhood to intersect with A is exactly the same as every neighborhood intersects with that, because those sets are the same. You see? So non-members of a set are close to the set exactly when they are limit points of the set. There is no distinction between the stronger condition of being a limit point and the weaker condition of being close to the set. Okay? I'm just checking my video. Suspicious. Okay. All right. Now I'm going to tell you something. Here is a further observation. And I'm going to say, we suppose that A is a set of numbers. We are going to show that if you look at A bar, what is A bar? What does this stand for? That's the set of all numbers that are close to A. Okay? I'm going to explain to you why A bar is exactly equal to, who knows what I'm going to write. Oh, I forgot to tell you something. I need notation. So sorry. I forgot to tell you the symbolism. The set of all limit points of a set A is written. I forgot to tell you how we write it. It's written, open a quote, the set of all limit points of the set A, close quote. You must be crazy. Can't write that all the time. It'll drive us crazy. So what do we write? Well, I'm going to write this. The trouble is you will think it's L for Lewin. Next time I teach 4381, I'm going to make sure all my students have a style file in their machines that will allow me to use a beautiful curly L here. Anyway, I'm stuck with that stupid symbol. All right. The set of all limit points of a set A is called Lewin of A. No, L of A, okay, is the set of all. So what numbers belong here? A number is there when that number is a limit point of A. There might be none, by the way. There might be no limit points at all. A set doesn't always have limit points. We'll talk about that in a minute. The set of those numbers that are limit points of a set A is called L of A. Now that I've got that thing off my chest, I'm going to tell you that A bar is always equal to A union L of A. We're going to see this. Okay? We have to write two proofs. We'll write a proof in this color, and we'll write a proof in the other greenish cyan color. Why do we have to write two proofs? Every time you want to prove that two sets are equal to one another, you're writing two proofs. You've got to show that every number in the one set must belong to the other set, and every number in the other set must belong to the one set. Sometimes you can squeeze them together. I'm too scared right now. I might mess up also. I'm definitely in a mood to mess up today. I'm not sure if I trust myself today. You have to watch me very carefully today. Maybe 6 more cups of coffee and I'll be reliable. Okay. So
For your next class?
the only trouble with drinking coffee, I'm not going to go into this. All right. So to show that A bar is included in the right side, A union L of A, how do you prove that every member of A bar does something? Suppose that X belongs to A bar, right? Okay. There are two cases. In the event that X belongs to A, we certainly have X in the right side. Isn't that right? If X belongs to A, it belongs to the union of A with something. You see? So we are done. But what happens if X doesn't belong to A? Now we assume that X does not belong to A. Does not belong. Now what? Well, so X is not a member of A. Well, for this X, the fact that X is close to A tells us that X is a limit point of A, because I told you a minute ago that for numbers that don't belong to the set, there is no distinction between being close to the set and being a limit point of the set. When a number doesn't belong, everything is good. All a number has to do is be close to the set. If the number doesn't belong to the set, then being close is the same as being a limit point. So here I'm saying suppose that X is close to A. If X belongs to A, well, it's here. So it's on the right side. See? If X doesn't belong to A, the fact that X is close to A makes it a limit point of A. So it belongs here. So are we done that the left side is included in the right side? Now we're going to take the other direction. So let's change color to show that this thing is a subset of A bar. Okay. Well, we suppose that X belongs to that. Yes? Okay. Perhaps X belongs to A. If X belongs to A, then of course X belongs to A bar. We've long since known that every number that is close to a set, every number that belongs to a set must be close to the set. The next one is fine. If X, well, what is the other possibility? You belong to the union when either you belong to A or you are a limit point of A. So if X is a limit point of A, then we also know that X is close to A. Isn't that because that's one of the first things I said today, is that limit points of a set are always close to the set. It's harder to be a limit point than to be close. So actually, the fact that the right side is included in the left side is the easy direction. The harder direction was that. Let me go through this part of the proof again. How do you prove that A bar is a subset of this? Suppose that x is in A bar. Now there are two possibilities. Either x belongs to A or it doesn't. If x belongs to A, there's no question x is on the right side because that's A union something. Suppose x doesn't belong to A. Now that's the tricky part. The fact that x doesn't belong to A tells us that for x to be close to A is exactly the same as x being a limit point of A, and so therefore I said x is close to A, so it's a limit point. This direction is the easy direction. Numbers here might belong to A, then they're certainly close to A. And if they don't, then they're limit points of A, and limit points of A are also always close to A. So we're done. You see? So we have this. Now I want to tell you something else. We're coming a little bit closer. Condition for a set A to be closed. I think we know that a set A is closed if and only if A is equal to A bar. What happened here? Equals. Yeah, A bar. This is something we did when we started studying closure. A set is closed if and only if it is equal to its closure. A set is closed if and only if. Listen, a set is always included in the closure. Isn't that right? A set A is always a subset of the closure because what? Every number belonging to a set will always be close to the set. But a set is closed if and only if the set is exactly equal to the closure, meaning that numbers that are close to the set have to belong to the set. It's always true that numbers that belong to a set are always, finish my sentence. It's always true that a number that belongs to a set is close to the set. But now, the condition when a set's closed, then every number that is close to the set has to belong to the set. And this is something we've done. Let me remind you, if set A is closed, a number that doesn't belong to A belongs where? Where do you live if you don't belong to A? Complement A. Complement A is open, so that gives you a neighborhood that doesn't intersect with A. Okay? If A is closed, numbers that don't belong to A will never be close to A. By the way, the other direction, if A equals A bar, why must A be closed? If I tell you that A equals A bar, I'm reminding you, if A equals A bar, why has A got to be closed? Because we had a theorem that if you have any set A bar is always closed, didn't we? In fact, I did it twice. I did it at the end of a lecture, and then I did it at the beginning of the next lecture, giving you what I call the direct proof, so that you had two ways to try to make you happy. Not really, to try to make me happy. I was a bit worried about the proof by taking compliments. I kind of looked at you and you looked kind of sad, so then I thought I better give you a direct proof next time. And I think that the direct proof went down better if you've rewritten it. You need to have taken that and rewritten it 3 times, 4 times, 10 times. I don't know. Some people no times, some people 10 times. I think that we know that a set is closed if and only if it equals its closure, right? Okay. Now, a set A is closed if and only if A is equal to A union L of A, because the closure of A is that. Is it not? Now, what makes these two equal? What makes this equation? What makes this equation hold? The right side is the union of A with some other garbage, right? What makes this equal to A? That all these guys have to belong to A. Isn't that right? I mean, if you know that this equals A, then all the points here have to belong to A. But if all these numbers have to belong to A, and then the union of this with A is just A, isn't that right? It's not giving you anything new.
It's like the reverse of taking out something that's not there to begin with.
Yeah, I mean, here's the point. Yeah. So here's the point. What objects get to belong to the union? Either in A or in Elevate. But if the members of Elevate happen to belong to A already, you wasted your breath even mentioning. I want to tell you, this is the condition that Elevate, the set of limit points of A, is a subset of A, that every limit point of A has to belong to A. This says that every member of that set must belong to A. A set A is closed if and only if every limit point of A has to belong to A. See? I'm showing you an example again. The number 3 is a limit point of the interval that goes from 1 to 3. Is that not true? The limit point is close to that interval and doesn't belong. It's actually a limit point. Is it not? Okay. And, of course, 3 does... Is that a 3? Try that again. 3... You think I'm going to bring in E today? Hell no. I wish I could. 3 does not belong to this interval. You understand? Well, that's okay, because this interval is not begins with C. Chicken. No, closed. See? A set is closed if and only if every one of its limit points belongs to the set. A set is closed if and only if this, which is the closure of A, is equal to A. This union will be equal to A if and only if all these guys belong to A. So I just wanted to make this point. Now I'm going to ask an interesting question. Here is a question. We suppose that I'm tired of A. Let's use an E or an S or something for a change. I'm sick of A. Then you think, oh, now you've got to change to E. Everybody will memorize. At this point, you mustn't use A. No. All right, I'm using A again. Okay? We suppose that A is a given set and that that X is a limit point of A and that delta is greater than 0. Okay? I haven't asked my question yet. We know from the definition Yeah, I keep saying of course. We know from the definition that the sets stick center x radius delta intersected with A and take x out of the picture is non-empty. Don't we know that? Now I'm asking my question. Can this set can't be the empty set, you understand? Can this set contain only one number? Only one number? That's my question. Intuition. Either I'm going to come up with a cute little example. I'll give you an example of a set A and a limit point x of A and a positive number delta, and I will say, look here, this set is not empty, definitely not empty, right? Not empty, but it's only got one number in it. Or alternatively, I won't give you such an example. I will tell you there isn't one, and I will give you a proof that this set must contain more than one number. More than one means at least two. You see? So before I do it, I have to ask you for your opinion. I need an opinion from you. What do you think?
Intuition says that it's impossible to have just one.
I've got one vote that says no, there can't be just one. I think I'm going to go for the no votes here. Who says I'm not going to give you an example, I'm going to give you a proof that there can't be only one? There can't be just one. What is that quote from Highlander? I'm trying to... it's the opposite, isn't it? Right? Let me see how many people are voting for that. I'm going to give you a proof that there can't be only one. 1, 2, 3, 4, 5, 6, about 10 people. How many people say Lewin is going to come up with a diabolical little example? I'm going to show you. Here's an example of a set A and a limit point x of A and a positive number delta, and lo and behold, in that set over here there will be only one number. How many people think I'm about to give you an example? I've got 4 votes. So by democracy, the noes have it, right? Of course, it all depends on which way I vote, right? No, it doesn't depend on how I vote. I am capable of making mistakes like anybody else. I've even made a mistake today. I'm not showing you right now. I'll show you on Monday. But I could be wrong as well. That's the difference between math and, say, fine art. You know, you paint your picture, a beautiful picture, you're so proud of it, and you hand it to the instructor and say, what do you think of my picture? And the answer is the History of the World Part 1. It's right at the beginning of the movie. You know, the first art critic, if you know what I'm talking about, right? So, so you know, it doesn't happen in math. I mean, if I call it wrong, I'm wrong too, you see? Okay. I want to change color. I need to say this and then we have to stop. To obtain a contradiction, we assume that this set over here, contains only one number that we will call y. Okay? I will get you a contradiction. And that's right, there can't be only one number, there has to be at least 2. All right. Actually, there have to be at least 3. Not quite ready to tell you that. Okay, so I'm going to get you a contradiction. On Monday, I'll tell you it has to be at least 5. What did I say? There have to be at least 5 million. There have to be infinitely many, actually. All right. To obtain a contradiction, we assume that this set contains only one number, and I'm calling that number y. I'm not choosing. There's only one, giving that one number a name. Call it Charlie or Y or something. Okay, I'm going to introduce a new positive number. We define, let's call this number delta 1 to be the smaller of the numbers. Actually, I don't even have to do that. I will. This is totally unnecessary. Sometimes you say something unnecessary because then you don't have to explain yourself. The smaller of the numbers delta and the distance from x to y. There was no need for me to say this. I could have justified delta 1 to be this. Please note that this number delta 1 is positive. Why? Because delta 1 is one of the numbers, this and this. How do you know that's positive? Well, not every absolute value is positive. An absolute value could sometimes be equal to?
It's not.
Could sometimes be 0. How do you know this is not 0?
Because you're saying y.
Because y belongs where? There, y is definitely not equal to x, right? So therefore, x minus y is not the number 0. It's either positive or negative, and the absolute value is definitely begins with p. Positive, right. So we know that delta 1 is positive. Okay? Okay. This set over here, but I'm putting delta 1. Now, the only number, delta 1 is not more than delta. Do you understand? The only number that could possibly be here, is y. Do you understand? Because delta 1 is not more than delta. You see? But y can't be here because y is not in that interval. Because how far is y from x? Exactly delta 1. And numbers in here have to be how far from x? The distance less than delta 1. If you want to live here, how far can you be from x? Your distance has to be less than delta 1. And how far is y from x? How far is y from x? Well, it's
12.
Delta 1 is less than or equal to that. You understand? Actually, to be honest, delta 1 equals that. But I don't want to explain. Delta 1 is the smaller of these two numbers. So delta 1 is not more than this. Do you understand? Is the distance from x to y less than delta 1? No way. Delta 1 is less than or equal to both of these numbers. The distance from x to y is not less than delta 1. So y is not here. Y is not here, you understand? The only number that could possibly be here is y, and y is not there. So you know what that set is. There was only one number that could possibly have belonged, and it doesn't belong. So therefore it's the empty set. And this contradicts the fact that x is a limit point of a, because I've got a positive number delta 1 and the stick center X radius delta 1 fails to intersect with A/singleton X, and they contradicts. So now I'm going to say, could there have been only one number? Not a chance. If there were only one, we could shrink the delta just a little bit and leave that one out in the cold. And now we've got the empty set. See what happened? Well, what if there were two numbers? We'll do this next time. You would shrink the delta again to get rid of the second one. What if there were 13 million numbers? Well, you just do this over and over again until you've shrunk it and shrunk it and shrunk it and kick them all out. We won't do that today. We'll do that next time. I will write this more systematically next time. That's it. I am stopping.